Okay, we're going to start with spectroscopy today. Hopefully everybody got notes on their way in. So what we're going to start with is this x-axis. What is it? What units is it in? And then we will talk about determining the numbers of different peaks that you're going to see in an NMR spectrum. And that's where there's going to be homework assignment for next week that'll be due. And I already put that online. And I'll put this lecture online if you need to go back and listen to it later on. So the issue is the y-axis here in an NMR spectrum is going to be related to the intensity of the peak, which is going to be proportional to the number of hydrogens that one has in that particular signal. The x-axis, the position of the peak on the x-axis is going to tell us about the shielding and de-shielding of those hydrogens, which is going to tell us something about the structure. But what units do we have on the x-axis? Well, we have units that are called the chemical shift. And the chemical shift is given an abbreviation of delta. And it's in parts per million, and I'll tell you where that comes from here. So the first thing is that we set 0 on that x-axis to equal the peak from tetramethylsilane, which is the compound that we had before break that I gave you a quiz on and asked you to show me why it's shielded. So the CH3s, the 4 CH3s attached to silicon, are going to give a peak, and that peak is going to correspond to 0 on our scale. So we just tell the computer that TMS peak is going to be 0. We will sometimes add a small drop of TMS to the sample, or there might be some TMS in the solvent that we use. But either way, we take the TMS peak and we say that's 0 parts per million, 0 chemical shift. Then we'll have a peak from our sample that will occur basically to the left of that reference. We choose TMS for a couple reasons as a reference. Number one, since it's shielded, most of the peaks in a normal organic molecule are going to be to the left of that. So it occurs really at the one end. And then that gives us positive chemical shifts. So we don't have to worry about saying, well, this peak shows up at -4 or -5. It just shows up at 4 or 5. The other thing is that TMS sometimes has to be removed from a sample if you add too much of it. So TMS boils at about 30 degrees. And so if you just let your sample sit out, the TMS would evaporate. But that's not much of an issue, or not as much of an issue as it used to be. So if we have this peak that corresponds to our compound, basically there's a difference between those two peaks that's going to be measured in hertz. Okay? For the most part, the differences between peaks in an NMR spectrum are going to be either hertz or fractions of hertz. It won't be more than maybe a couple thousand hertz, but it's not megahertz. That's the key. And we have a problem in defining the x-axis, because if I'm going to measure the position of this peak in hertz, what I know is that when I go to stronger and stronger magnets, or if I go to a different magnetic field, that Larmor frequency where the nucleus precessed is going to be proportional and change. So my peak position in hertz is going to be different on a 60 megahertz instrument versus a 300 megahertz instrument versus a 900 megahertz instrument. And when they first came up with this idea of the x-axis and the chemical shift, what they decided to do was to make it so that the chemical shift would never change as you got stronger and stronger magnets. And so what we do is we define this chemical shift down here as basically the position of the peak minus the position of TMS in hertz. Well, the TMS position is always going to be 0 because that's our reference. And then we're going to divide that difference through by the operating frequency of the instrument. In other words, the overall Larmor frequency of the nucleus, which is in megahertz. So for our instrument, protons have a 300 megahertz Larmor frequency. The difference between the two peaks is like 300 point and then like 6 decimal points. Okay, it's in terms of hertz. So let's say that this peak right here is 300 hertz away from TMS, that the difference there is 300 hertz. And the chemical shift then of this peak would be that 300 hertz minus the TMS reference. Okay, so that's in hertz. And then I divide through by the operating frequency of that nucleus, which, our instrument, if this is a proton, would be 300 megahertz. Okay. And so what would I get? Well, I'd get 300 hertz over 300 megahertz, which is going to be then 1 hertz per megahertz. And now you can see where the part per million unit comes from, because a hertz and a megahertz is 1 part in a million. Okay. So that peak, this peak would show up at a chemical shift of 1. And it will always show up at a chemical shift of 1. Because if I now take that sample to another instrument that has maybe a 600 megahertz magnet, the difference between the two peaks will now double because the Larmor frequencies have doubled, and then the operating frequencies doubled, so they cancel out.
So does the machine do this and it's automatic? Does it do this and show up at 1? I'm confused. What does the 1 mean?
The 1 is the position. If I go back here to, that means that, let's say here's my chemical shift. Here's my spectrum. So 0 is where the TMS peak would show up. And then let's just say, for the sake of argument, that I've got a peak that's 300 hertz away from 0 on a 300 megahertz instrument. Well, that peak would show up at 1 part per million. When we look at the scale on an NMR, all we're going to see are numbers from 0 to 12. Well, 1 means 1 part per million, which on our instrument means that that peak is 300 hertz away from the 0 TMS. On a 500 instrument, it would mean that they are 500 hertz away with an operating frequency of 500 megahertz.
So it's always going to show up at the same?
It's always going to show up at 1, yes. That's the key. A peak will always show up at the same chemical shift regardless of the magnetic field. If you make it smaller or bigger, it will always have the same position on that axis. So in a way, that's what the instrument does, is the instrument calculates the chemical shift and then gives it to you. I'm just giving you an example that I didn't have to do much math with. Okay, 300 over 300. So the chemical shift position of that peak doesn't change, regardless of the instrument. And that was a pretty insightful move by whoever came up with this, because they anticipated stronger and stronger magnets and immediately made a correction and said, we need to make this scale so that it will never change. And then that way you can go back and you can look at an NMR from the 50s, and all the peaks will be at the same positions on the chemical shift scale as they would on a new 900 megahertz instrument. As we go through the rest of the semester, we'll find out that a spectrum from the 50s is going to be pretty worthless, but not because the peaks don't show up at the same chemical shift as they do now, but for other reasons. Okay. So the chemical shift scale then is independent of magnetic field strength. And as we go through, we're going to find a number of different things that will depend on the magnetic field and those that don't. Chemical shift doesn't change. Larmor frequency of the nucleus, though, it does. Okay. So that's what the x-axis is. Everybody kind of with me? And the point is this, that then what we can do is then we can take our molecules and we can start recording the positions of the peaks and come up with correlation charts that'll tell us where we're going to find protons depending upon what kind of shielding or de-shielding they have. So for instance, if you have a carboxylic acid proton, that's going to show up between 11 and 12. If you have an aldehyde proton, that's going to show up between 9 and 10. If you have a benzene ring, that's going to show up between 7 and 8. If you have hydrogens that are attached to double bonds, are going to show up between 5 and 6. Hydrogens that are attached to carbons that are attached to electron withdrawing groups are going to show up between 3 and 4. That was our example of de-shielding. And then just your normal run-of-the-mill alkane hydrogens that don't have any particular extra de-shielding are going to show up between 1 and 2.
Are those heights on there arbitrary, or is that going to be the actual?
No, the heights of these bars is just to fit them all in.
Okay.
It's just to fit the structures.
So the peaks could be.
Yeah, no. What we're going to find next week is the height of the peak is just like GC. It's proportional to the number of hydrogens in that signal. So all these bars are telling us is where we're likely to find the peaks. And there's different correlation books in your, or different correlation tables in your textbook. Computer programs will tell you what chemical shift you should find, hydrogens, if you draw in the structure, and there's tons of tables that'll do that. So yeah, it's just to fit all the structures, and you've got to like put them in different places. Rob.
So basically we look at where the hydrogen is, and where that shows up on this chart is going to tell us what kind of molecule we have. So it's another way of...
Well, it's correlation. And everything's been done by correlation. So if after you have the peak positions of 2 million compounds, you can begin to predict, just simply by correlation, of where hydrogens, if they're attached to a certain group, will show up. Then you run a spectrum of your compound that's unknown, the structure's unknown, and then from the position of the peak, you go back and it'll tell you something about the structure of the molecule. So that you have to have a correlation table first before you can go back and analyze an unknown compound. We're going to start today by predicting how many peaks we should see. And then we'll look at shielding and de-shielding as we go through the rest of the weeks. Right. So you don't have to worry about memorizing this table simply because I will give you a much cleaner version of this table as we go through. But on the final exam, I'll give you this. You just have to know what to do with it. But when we get to looking at unknown compounds, if you see peaks at 7, between 7 and 8, benzene ring. This is better than IR, where peaks above 3,000 indicate double bonds that are present. We couldn't tell there whether it's a ring or a double bond. Here, if it's between 7 and 8, it's a ring. Between 5 and 6, it's a double bond. So we'll talk more about the structural aspects of it, but that's the chemical shift. If the peak position changed as a function of magnet, we wouldn't be able to use stuff from 20 years ago, and we wouldn't be able to use what we have now 20 years from now. So the idea is, because we're taking a ratio, the chemical shifts will stay the same in the future. So all these tables are still valid. That's the important thing. I would have given the people the Nobel Prize just for that, just for thinking that far in advance. But now what we need to do is now we need to sort of, from a structure, predict how many peaks I would see in my NMR spectrum. And we have a term for this, and it's called chemical equivalence. So hydrogens that are what we call chemically equivalent have the same chemical shift, meaning that they will show up as a single peak or have a single chemical shift in our NMR spectrum. That's what being chemically equivalent means. And there's a couple of different ways to determine whether two hydrogens are chemically equivalent or not. Or to look at a molecule and say, I'm going to have 4 peaks because there are 4 sets of non-equivalent hydrogens in my molecule. And the first has to do with looking at symmetry. So 2 hydrogens will be chemically equivalent if they can be related by a mirror plane of symmetry. Now this kind of is the same mirror plane of symmetry that you used for meso compounds, or to try and pass through a chiral center to then show that it's not chiral. But it's going to be much broader than that. So let's say I have propane here. And if I have propane, I'm going to write out its Lewis dot structure to make the mirror plane much clearer. But if you had propane and I asked you, well, how many sets of non-equivalent hydrogens are there? In other words, how many peaks am I going to see in the spectrum? Assuming that peaks that are even slightly different can be resolved. I can see them. I'd look at this molecule and I'd say, is there a mirror plane of symmetry that I can pass through this molecule that would make hydrogens equivalent to each other? Actually, the way I've drawn the molecule here, I see 2 mirror planes of symmetry. Right? I see mirror planes of symmetry. I see a mirror plane of symmetry that could go this way through the molecule, which would then make the CH3s would make this H equivalent to this one, this H equivalent to this one, this H equivalent to that one. They would be different than the CH2 that way, okay? Because there's no way CH3s. In all of this, a CH3 will never be equivalent to a CH2. A CH will never be equivalent to a CH2. Okay, 2 CH2s may be equivalent. 2 groups of CH2s. So there's one mirror plane that way, but then there's also a mirror plane this way as well. So the mirror plane that way would say that this hydrogen is equivalent to this hydrogen is equivalent to that, this hydrogen is equivalent to that. Okay. If I pass the mirror plane through the molecule written down here in its condensed structure, I could say, and I'm just going to rewrite it down here to make it a little bit clearer, but I'm going to say, okay, if I pass the mirror plane like that, this CH3 is equivalent to that CH3, but different than the CH2. So that's one way we can use mirror planes to try and figure out whether hydrogen groups are equivalent to each other. So the 2 CH3s are equivalent to each other, and the CH2 is different. So that's one way to look at a mirror plane. Sort of that's similar to this is to look at the ball and stick model of propane. And if you imagine that a mirror plane would cut this molecule in half and the mirror plane would be the screen, then this hydrogen is mirror plane of that, this hydrogen's mirror image of that, this hydrogen's mirror image of that one. And so in that case, those hydrogens would be equivalent to each other as well. So we can use mirror planes to determine which hydrogens are equivalent. If they can be related by a mirror plane, they are chemically equivalent, which means that they will show up at exactly the same chemical shift. And therefore, there will be a single peak that corresponds to that group of hydrogens. Okay. So mirror plane is one thing we can use. Then another thing that we can use is what's called rotational symmetry. And the rotational symmetry comes about, the easiest way to see this is to think about a methyl group. And the idea that if you take a methyl group, which can be approximated by 3 fingers, if you rotate around the methyl, if you rotate around that bond, I can rotate this hydrogen into this one into this one's position, and then this one into that one's position. So at room temperature, where you've got lots of energy and lots of different conformations, those 3 hydrogens can be rotated into each position, which is going to make all the hydrogens equivalent to each other by rotational symmetry. So before with the propane, we had these mirror planes, but what we can now see is because of rotational symmetry, CH3 hydrogens are all going to be equivalent to each other. So we can look at that as a way to determine that two things are equivalent as well. All right, so that's another thing we can use. And then the third is the idea of not of symmetry, but of what's called conformational equivalence. So conformational equivalence is most often seen with cyclohexane rings. Okay, so let's say we have a cyclohexane ring like this, and we know that our equatorial hydrogen and our axial hydrogen might be in slightly different electronic environments. And they might be slightly differently shielded and deshielded. But you also know that a cyclohexane chair can undergo a ring flip. Right? You can take the chair and you can turn it into the boat, and then you can flip the chair around. Right? This is one form of the chair, and then you've got like the left-handed version of the chair as well, or the right-handed version, depending on what you are. We've got those two versions. Bless you. So if cyclohexanes have enough energy at room temperature, they're constantly undergoing ring flips. And from last semester, hopefully you remember that when a molecule undergoes a ring flip, the axial hydrogens become equatorial and vice versa. So at room temperature, if that chair cyclohexane can be flipping back and forth very easily, then what we'll see is those two hydrogens will basically average out, so that we'll only see one hydrogen with one chemical shift. Now, that depends. This sort of phenomenon of how quickly it flips is going to invoke what we call the Nmr Time Scale. Okay? And the Nmr Time Scale basically is how fast does the experiment take. It's kind of like taking a picture. If you want to stop the action, you use a very fast shutter. Right? Use a very quick shutter. If we still use shutters even though we use digital cameras. Okay, so if we open and close the shutter really quickly and we're trying to take a picture of a basketball that's in flight, then it'll freeze the basketball out and you'll be able to read it and see all the stitches and everything else. On the other hand, if you slow down the shutter and you allow the shutter to open and there's a big time gap, then all you'll see is the blur of the basketball. Well, the same thing's true here, except I don't change the time frame. The time frame is fixed. So the Nmr time scale is roughly on the order of a couple of seconds. So if in that couple of seconds these hydrogens are flipping back and forth between axial and equatorial, all I'm going to see is the blur. And the two hydrogens basically are going to have an average chemical shift that will be the average between these two positions. On the other hand, if I slow them down by reducing the temperature, and over that course of a couple of seconds they're stuck and they don't move, then I'm going to see two individual peaks, each having a slightly different chemical shift. So today what we're going to say is for the cyclohexane chairs, that all of them are able to flip back and forth a lot, so that we're going to treat these two as if they had the same chemical shift. But there is a dynamic part of NMR where you can change the spectrum by lowering the temperature and making the molecules basically stay static during that snapshot of the instrument, which is a couple of seconds. So we're going to say for conformational issues that a chair cyclohexane gives you the same one. Okay? So those are three things that we can look at to decide whether two hydrogens are equivalent. And those aren't necessarily the easiest things to do. So for instance, let's do some examples here. How many peaks would I see for butane in the NMR spectrum? Another way that I'll ask that is how many non-equivalent sets of hydrogens are in butane? So you can give me a number from 1 to 10. 4. 5. 2. We don't just randomly pick numbers. They should have a reason behind them. If you would like to randomly pick numbers, then bring something lucky to your final exam. 2. What was my question? My question was, how many sets of non-equivalent hydrogens are there in butane? In propane, there was 2. The CH2s were one set, and the 2 CH3s were equivalent, and they were a second set. And the answer is 2. There would be 2 peaks in the NMR spectrum of butane. Or I'm gonna bust that next week. But there would be 2 sets of chemical shifts in the NMR spectrum of butane. So what's equivalent to what? Well, first of all three of the hydrogens in the CH3 are equivalent to each other, right? Because of the rotational symmetry. And because of a mirror plane, the CH2s are all equivalent to each other. The CH2s that are attached to one carbon are also equivalent to each other. And then what I can say is, here's a mirror plane between butane, and now what's true? The 2 CH3s are equivalent, and the 2 CH2s are equivalent. So if all the CH3s are equivalent, and the CH3 is equivalent to the other CH3, that makes them all equivalent. If the 2 CH2s are equivalent, then being equivalent to the other CH2 is also making them equivalent. So we would have an A and then a B, because I like to label the sets that are not equivalent to each other with a letter. Okay, so we would see 2 peaks in the NMR, or 2 sets of chemical shifts in the NMR of butane. Does everybody see that? I mean, we're going to do another set of experiments. Pentane. How many? 3. Any other numbers? 2. 4. So I got a 2, 3, 4. Somebody want to go for 5? Is there a mirror plane in this molecule that you can draw? Yes. That makes what? The CH3's equivalent, right? So that makes The two CH3s are now equivalent to each other, so there's the first set. It makes this CH2 right here equivalent to this CH2, so that's a second set. Are those two CH2s equivalent to the middle CH2? No, because I can't draw a mirror plane that would make the middle one equal to the ones on the outside. So it's its own set, which is C. So there's three sets. So there would be three sets of chemical shifts. Now, these mirror planes are sometimes hard to use. The rotational thing's hard to use. Everything's hard to use. So let's look at this from another standpoint. And that is that for this one, what the answer was 2. That's the same answer that you would get if I asked you this question. How many unique products do you get if you do free radical halogenation on butane? How many unique products are there? Assuming one bromine substitutes for one hydrogen. Two. Well, I told you. I said it's the same answer as what we had above, which was 2. So another method to determine whether two hydrogens are equivalent to each other is to say this. If I want to know if these three hydrogens are really equivalent to each other, why don't I replace them one at a time with a bromine? So I'll replace one hydrogen with a bromine, name the compound. Then replace the other hydrogen with a bromine, name the compound. Replace the third hydrogen with a bromine, name the compound. Okay, I'm not replacing one and then I'm replacing one at a time. So I'm replacing the first hydrogen with a bromine, naming it. 1-bromopropane, or 1-bromobutane, sorry. If I replace the other hydrogen with a bromine, okay, the other bromine's not still there. If I replace the other hydrogen, I get 1-bromobutane. If I replace the third hydrogen, 1-bromobutane. Okay? So if I replace any of these hydrogens, any of these single hydrogens with a bromine, I get the same name. If I replace any of these three hydrogens with a bromine, what do I get? Same name. So that makes those two CH3s equivalent. If I replace either of these two hydrogens with a bromine, what do I get? I get 2-bromopropane, or 2-bromobutane, which is now different than 1-bromopropane, or 1-bromobutane, which makes these different than these. But if I replace this one with a bromine, I still get 2-bromobutane, which makes these two guys equivalent. Okay, so there's another method of determining equivalent hydrogens. You replace each hydrogen sequentially with a bromine, name the compound, same name, equivalent. Different names, not equivalent.
So like those two methyl groups on the ends, aren't they always going to be equivalent? Like what is a case if they wouldn't be?
When is a case when they wouldn't be? Okay, there's my next problem. How many sets of non-equivalent hydrogens are there here? Four? I should start calling on people. Then it's like be picking on people and their feelings would be hurt and their esteem would be crushed. 5? So I got a 4 and a 5. What? 6? Did you just say that, or?
This one's beyond my
How can it be beyond your knowledge?
I got the other two listed. I don't know.
5? Okay. Well, let's figure this out. First of all, CH, there's no other CHs, so that's definitely 1. There's no other CH2s, so that's definitely 2. So really what it boils down to is this. It boils down to whether or not any of those remaining CH3s are equivalent to each other. Okay? Now, how about the 2 left CH3s? How about this one and this one? Are they equivalent to each other? Yes, they are. When you have 2 CH3s that are attached to the same carbon, they're going to be equivalent to each other. Some people think about, well, I could rotate one of the CH3s into the other, which would make them symmetric. But if we just take the rule, okay, let's replace one of these hydrogens with a bromine. So that would give me 1 bromo, 2 methyl butane. If I replace one of these hydrogens with a bromine, I still get 1 bromo, 2 methyl butane. So those 2 methyl groups are equivalent to each other. And if you don't like that, then draw the molecule this way. There's nothing wrong with that. Now what have I done? I made it so there's a mirror plane to show them that they're equivalent to each other. Okay, after you do a few of these problems, you kind of get the hang of it. Okay, this problem is no different than what I asked last semester in lecture when I asked write all the different free radical halogenation products for a reaction. Okay, if you've ever had to do that or choose what products are formed, you're doing the same thing. So these 2 are the same. These are C's. Now, are they equivalent to this and CH3? No. Can you draw a mirror plane and make them equivalent? No. If I put a bromine at the end here, this would be 1 bromo, 3 methyl butane. Before it was 1 methyl, 2, or 1 bromo, 2 methyl butane. I mean, okay, this requires that you can name IUPAC named compounds. But at this point, that's the least of your worries in terms of lecture. That starts being less important once we get to things like reactions, reagents, and mechanisms. But these are alkanes. Okay, so in this case I got 4. So that was the correct answer, was 4. If you said 5, you thought the 2 methyl groups were not equivalent. If you said 6, don't know what you're thinking. Okay. All right. Methylcyclohexane. How many sets here? 3?
Sure.
2?
I'm going to go with 4.
4?
Yes.
So we got a 2, 3, and a 4. 5? I like 5. Definitely the CH3 is 1, right? because there's no other CH3s in the molecule. I also like this. I also like that hydrogen there that you may have to put in. No other CHs in the molecule, is there? Nope. So that's a B. Now, how about the other ones? Well, if they're cyclohexanes and they're flipping back and forth, then all the CH2s are going to be equivalent to each other. I mean, the axial and the equatorial are going to blend together to form one chemical shift. But can I not do a mirror plane this way through the molecule so that this is the same as this, and this is the same as this, and then that is its own group? If I put the mirror plane through the molecule like that, is D going to be equivalent to C? Only if I could draw, the only way that C and D are going to be equivalent to each other is if I can draw a mirror plane like this through the molecule. Well, I can't do that. So they're not going to be equivalent. E's not going to be equivalent to B, because one's a CH2, one's a CH. So in this case, there's 5.
So does that mean that there's going to be 5 peaks between 7 and 8?
5 peaks between 7 and 8. No.
So what does this 5 mean again?
What this 5 means? Well, let me deal with the 7 to 8 issue. Okay. There's not going to be any peaks between 7 and 8, because 7 and 8 is a benzene ring. And a benzene ring has the alternating double bonds or the circle in it. This is just cyclohexane. So for cyclohexane, these chemical shifts are probably going to be between 1 and 2, or 1 and 2.5. Okay? So that deals with the 7-8 issue. What it means is this. It means that in my NMR spectrum, I'm going to see 5 different chemical shifts. That's what it means. 1 for the CH3s, 1 for the CH, 1 for the BCH2s, for the C, or 1 for the CCH2s, for the DCH2s, and for the ECH2s. That's what it means. I'm going to see 5 sets of peaks, each having a slightly different chemical shift. Now the reality is that they're all going to smush together, and then we have this small issue of splitting to deal with. Okay? So that's what the 5 means. It means there's 5 different chemical shifts that I'm going to see in the spectrum. But we got to start somewhere. So this is the idea. There are 5 sets of chemically non-equivalent hydrogens. There's 5 sets of peaks that are not equivalent to each other. Next. Alkene. Four. 5. 3. Not liking that answer that much. 12. What can we... Any mirror planes I can draw on that molecule? No. Can't draw any mirror planes. So that must mean that this CH3 is on its own, this CH2 is its own group, this CH3 is its own group, this one is its own group, and this one is its own group. So that makes 5. Now, if you said 4, you might have been intending that these two hydrogens were indeed equivalent to each other. But they're not. Okay? If I replaced this hydrogen with a bromine and named it, it would be the E isomer. Right? If I replace this hydrogen with a bromine, then it would be E because the bromine would be trans to the ethyl group. If I replace this hydrogen with a bromine, it would be the Z isomer. Okay, if we name things E and Z. So in that case, those two hydrogens are different. So we have 5 different hydrogens, 5 sets of hydrogens. Which means in the NMR spectrum, the chemical shift of this hydrogen is going to be different than this one. Bless you.
Except because it doesn't rotate with the double bond.
Right, double bonds don't freely rotate. And there's no mirror plane that will make them the same. All right. Final problem. Cyclohexane. How many peaks? How many sets of non-equivalent hydrogens? 1? 4?
They all equivalent? 0?
Can't have 0. You can't have 0 peaks unless there's absolutely no hydrogens in the molecule.
All right. I'm going to go with 1. My bad.
3?
3.
How about 1? I would have thought the 1 somebody would have gone, oh. Apparently not. Now, this is one where if I replace any of the hydrogens in that ring, what am I going to get? If I use the replacement of a hydrogen with a bromine, if I replace the hydrogen here, what do I get? Bromocyclohexane. If I replace it here, what do I get? Bromocyclohexane. So any of those hydrogens replaced with a bromine gives you bromocyclohexane. But if you don't like that, then look at this. In this case, look at all the mirror planes. You got a mirror plane this way. That makes these two guys equivalent, these two guys equivalent, and these two guys equivalent. But now if this one's equivalent to this, then when I draw my mirror plane this way, all of a sudden this one's now equivalent to this one, which made this one equivalent to this one, equivalent to this one. But wait, now there's a mirror plane here, which makes this one now equivalent to that one, which is equivalent to this one, which is equivalent to this one, and they're all equivalent to each other. Right? That you can have multiple mirror planes that do that. So in this case, there's 1 peak for cyclohexane. Okay. Assuming that the cyclohexane is ring flipping back and forth, and the axial and the equatorial are basically merged together. So in that case, it's easier just to say, replace the hydrogen with the bromine and name it. Unless you want to see all those mirror planes. And that works too. Okay. All right. So that's what I'm going to ask you to do for your homework problems. Is take the molecule and then assign each group of hydrogens with a letter. And in essence, you're telling me how many sets there are. So in this case, all of these guys would be A's because they're all equivalent to each other. So I would say there's 1 set, all A's. So you can go A, B, C, whatever letter you need to use. If you think 2 hydrogens off different groups are equivalent, there better be a mirror plane that relates them. If there's no mirror plane, then chances are they're not equivalent. It's kind of like doing chirality and meso, kind of. Okay, so that's your homework problem problems for next week, and I'll collect them up next week. I already put them online, and I've also put the master copy of all the PowerPoint slides online. I will put this lecture online once it all gets compiled, as long as I push the right button.